This is Mr. Hunter, and I'm going to do a wee rates of reaction revision, and hopefully this will be useful for your final exam. I'm hoping it won't be any more than about 12 minutes. So let's get down to business. Okay? So first thing I want to look at is how to measure the rate of reaction. And when we're measuring the rate of reaction, you need to look at some chemical reactions which have something changing over time, because the rate of reaction is a measure of something changing over time. So for example, if we take calcium carbonate and acid, and you should all know by now, of course, that you get a salt and water and carbon dioxide, then this is a gas. Now, because this is a gas, we could measure the volume increase by connecting up this experiment. Here's a little conical flask, and my diagrams are awful, you know that, but never mind, you'll get the idea. Here's a big syringe which is going to collect all that gas. Okay. And if you have a clock, you can measure that every 10 seconds. That's your little stopwatch. So you could measure this reaction and the gas it forms every 10 seconds. And then you could graph it. You could graph the volume of the gas in cm cubed. Oops, not very nice, but never mind. And you could measure the time. And hopefully it would look something like that. Now we're going to come back and look at these graphs later, and they'll be much nicer as well. You could also look at this experiment by putting the experiment on a mass balance and measuring the mass loss, because the CO2 is going to be released to the atmosphere. So because of that, you lose mass. And you could chart that over time. That would be a graph of grams over time in seconds. And it would go down like this a little bit. Not very good, not very well drawn, but it would end up flat line. Not necessarily zero, of course. So here we have some graphs. And for example, this graph could be volume of gas on the y-axis. It could be for the previous experiment we looked at, and this could be time on the x-axis. And we've got three graphs here. We've got graphs number 1, number 2, number 3. Now, I just want to consider graph number 3 firstly. So, ask yourself, where is the graph fast? Where is the rate fastest? Okay, where is the rate fastest? Now, I'm hoping you said here. Whoops, I'm hoping you said here, because this is where the initial rate is fastest, because the gradient is quicker. Hopefully you can see that the gradient is not as steep here, and I have to stop drawing arrows because of that, because it's not very good. And the gradient here is 0. There is no gradient here. So the reaction is fastest here. It's slowing down here. And it has stopped here completely. It's fastest here because the gradient is the steepest here. The gradient is the steepest here because the rate, the tangent at that point, is the fastest because the particles are at their highest concentration. As the reactant particles get used up, the rate slows down. Therefore, the gradient gets less. And as the reactant particles, or at least one of the limiting reactant particles, is used up, the reaction stops completely. Okay? Now, if we look at reaction 2, the same volume of gas is given out at the end. So we must have the same molar quantities of stuff. However, the rate is less steep. So hopefully you can see with the less steep gradient that the reaction is slower. The rate is slower. Another way to consider that is if you look at when the reaction is finished. For reaction 2, the reaction finishes about here. Well, here really. But for reaction 3, it finishes here, much earlier, so the reaction is quicker. Reaction 2 is faster. Why is it is slower? Sorry. Why is it slower? Well, we can see from the graph it's got a lower gradient. Chemically, why it's slower? Well, it's probably got a lower concentration or higher particle size, and we're going to discuss that in the next couple of slides. We're going to come back to graph 1 later. It is not only slower than 2 and 3 because it has an even lower gradient, so it's the slowest experiment of them all. It's the slowest rate. It also has half of the molar amounts. So the number of moles of reactant particles here, or at least the number of moles of limiting reactant, is about half. Okay? Now we're going to go on and talk about particle theory and why things react faster than others. Okay? So, what things change the rate of reaction? Well, if we change the concentration of solutions reacting, we change the rate. If we change the pressure of gases reacting, we change the rate. If we change the temperature, we definitely change the rate. It's actually a very special consideration. And if we add, or if we change the surface area, that is the particle size, we will change the rate. Finally, the addition of a magic substance known as a catalyst will also change the rate. So let's have a look at how each one of those will change the rate. Now, what do things need to react? Well, for two things to react, they must, remember, what must they do? That's right, they must collide. So they must collide, and the more that they collide, the higher rate you're going to get. So if you want to increase the rate of reaction, you need to increase the rate of collisions between reactant particles. In addition to that, if you increase the energy with which they collide, then it will also increase the rate. So let's look at each of those examples in turn. Number 1, concentration. Here we go. Right, here is a very crude diagram showing you two beakers. The beakers are supposed to be the same size, but they're not, but never mind. Let's assume they've got the same amount of liquid in them. This one has got 1, 2, 3, 4, 5, 6 reactant particles in it. And this one's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. This one has got a certain number of reactant moles in a certain volume, moles per dm cubed. But now you've multiplied this one by 2 because there's 12 reactant particles in here. So your concentration, or your moles per dm cubed, is higher. You have more reactant particles per dm cubed. Because of that, you have more collisions, and because you have more collisions, you have a greater rate of reaction. Isn't that right? Yes, it is indeed. Cool. Okay, so next, gas pressure. Well, gas pressure is exactly the same as the volume one that we said before, but this time it's for gas molecules. And the gas molecules, well, here I've got 5, and here I've got 10. So these 10 react more than those 5 because there's more collisions and there's a faster rate. Okay? So, the next one is particle size. Now, particle size is, again, it's all about collisions. Rates is all about collisions, collision theory. If you take, a good example is this, if you take a cube, now this cube has got sides of 2 by 2 by 2. So, each square here has a surface area of 2 by 2, 4 cm squared. Now, hopefully you can therefore see there's 6 sides to a cube, so the total surface area here is 6 times 4, which is 24 cm squared. Now, let's half this cube of reactant particle. I'm going to half it along there. Chainsaw down the middle here. Yes, I know it's childish, but not mind. I'm going to cut it down here as well. Okay? Now that will give you, if you can maybe stop, you can stop the podcast now. Stop. Well, don't stop yet. I'll ask you a question. How many cubes will you now have? Stop. Okay, hopefully you managed to work out that you're going to have 8 little cubes of 1 by 1 by 1. Sorry about the bad diagram. 1, 1, and 1. Now this therefore has, each side here is 1 cm squared. There's 6 of them. 6 times 1 is 6. But you've got 8 of them. 8 times 6 is 48 cm squared. So, the point of this is if you decrease the particle size, you increase the surface area, you increase the frequency of collisions, and you therefore, what's it all about? You increase the rate. So, why temperature increases the rate of reaction is really quite straightforward. When you increase the temperature, you increase the kinetic energy of the reacting molecules. That's effectively what an increase in temperature means. That means kinetic energy is a half mv squared, so you increase the temperature, you increase the velocity, so the particles are moving faster. If they're moving faster, they collide more. They collide more with each other. Because they collide more with each other, there's more frequent collisions, the reaction rate increases. But those collisions also have more energy. Because they have more energy, they have more than the minimum energy to react. That minimum energy is known as the activation energy. So, there's 2 reasons why temperature increases the rate. 1, they collide more. 2, they collide with more energy or more force, enough to overcome the minimum energy for reaction. Finally, catalyst. So, a catalyst, well, you probably all know the definition. A catalyst is something that speeds up the rate of a reaction, but is not used up itself. Now, why does it do that? It does that by reducing the activation energy. So you've got a smaller little hump to get over here. So, if you use a catalyst, you require less energy to get the reaction going. Examples of catalysts that you may have used in the class: manganese oxide catalyzes the decomposition of hydrogen peroxide to water and oxygen. Remember that reaction where we made lots of bubbles and lots of different colours? Well, that was using this catalyst. Also, biological catalysts. Well, biological catalysts are called enzymes. And there's plenty of enzymes in your body. Most of them are proteins. Finally, the catalytic converter in the car takes acidic nitrogen oxides and toxic carbon monoxide and turns them into carbon dioxide and nitrogen. And the catalyst to do that is platinum and rhodium. So this is much better for the environment. Okay? So to finish this little podcast, guys, I just thought we'd go back to this graph here and consider the reasons why these reactions may be different. Well, in reactions 2 and 3, it could be the case that 3 is done at a much higher temperature, maybe 20 or 30 degrees higher, but you've got the same number of moles. Or it could be the case that 3 is at a higher concentration, but note that if it's a higher concentration, you still end up getting the same volume of gas, so you're going to have the same total number of moles. Possibly, number 3 is something like powdered calcium carbonate, and number 2 is marble chips. Reaction number 1 is a slower rate than all of the two above. So maybe it's at a much lower temperature, but also it has a much lower total volume of gas here. So there's half the number of moles. You could also say that maybe possibly reaction 3 is using a catalyst compared to reaction 2. There's a bunch of things that could work out here. Okay, that's this podcast on rates over. And do the practice questions when you prepare for your exam. That's all for now. Cheerio!